Hello and welcome to NASA Ames Research Center. Today, the science team from the Lunar Crater Observation and Sensing Satellite Mission, or LCROSS, is presenting their initial findings from the lunar impacts on October 9th, 2009. On the panel today are Anthony Cole-Preet, LCROSS project scientist and principal investigator, Greg DeLaurie, senior fellow at the University of California, Berkeley's Space Sciences Laboratory, Michael Wargo, chief lunar scientist for NASA headquarters, Washington, and joining us remotely from NASA headquarters, Doug Cook, associate administrator for Exploration Systems Mission Directorate. After each has spoken, we will take questions from reporters in the audience and then remotely on the phone. Before we begin, Dr. Pete Worden, Center Director for NASA Ames Research Center, has a few words. Sir?
Good morning. It's been a great week for NASA. If you don't know, Time magazine identified a couple of our programs as the top inventions of the year, including our Ares rocket, so we're pretty pumped. It's also a great Friday the 13th, and it's a great day, another great day for NASA and NASA Ames and our colleagues at all the other centers and at NASA headquarters and our colleagues in industry. Just a little over a month ago, we were here giving you the preliminary results from the LCROSS mission that showed that we had a lot of really good data. Well, the team has been working, I think, about 28 hours a day. I'm amazed they look as bright-eyed and bushy-tailed as they are, but they're back here to share some really exciting results. These will add to our understanding of the moon. They will enable NASA to plan future missions, including eventually human missions to the moon, and they open a new chapter in our knowledge about our nearest neighbor. Today's announcement is exciting not only for NASA and the scientific community, but also for explorers everywhere. Now, without further ado, I'd like to turn it over to those that made it happen. Tony?
Thank you, Pete. Thank you. It's good to be here again. As Pete mentioned, about 1 month ago, we made an impact, and we saw some squiggly lines, and we've been working about 28 hours a day, a large team to understand what those mean. And so I'm here today to tell you that, indeed, yes, we found water. And we didn't find just a little bit. We found a significant amount. If you remember, about a month ago, we were talking about teaspoons going to glasses over football fields. Well, now I can say today that in the 20 to 30 meter crater LCROSS made, we found maybe about a dozen of these 2-gallon buckets worth of water. So this is initial results. It's preliminary. You're going to hear how we came to this conclusion today. I'm going to walk you through it. And it's probably a lower bound on the total amount of water we've seen here. And there's a whole lot more beyond the water. So that's the exciting part in my mind, is it's not only about the water now. There's actually a lot more here that we're going to be talking about in the months ahead, looking at the LCROSS data. So it's a very exciting time for us. The science team's been working exceedingly hard. I'm very honored to be a part of such an awesome group of people who've really been working pretty much nonstop for the last month to look into the data. And you'll understand why it's taken us a long time to come to some of the conclusions here in a minute. So what I'd like to do is bring us back a month ago. I probably was a little more tired than I am now then. But and pick up where we left off with the curtain, what we saw with the ejecta cloud, and then just step you through some of the points of analysis that we did to come to the conclusion that I just asserted. So with that, let's go to the first slide. The first slide will show a visible camera image of the ejected cloud. This is an image that was about 20 seconds after impact. We saw a nice plume rise. It was, in this particular image, the inset shows to the lower left the plume. It was about 10 to 12 kilometers across at this point. This camera, we weren't very hopeful of actually seeing the ejected cloud, so we were quite pleased that we saw it. It was a nice, large plume that came up. In the next slide, it shows the approximate field of view of the instruments that I'm going to talk about that did this water detection I just described. The red circle there shows a 1-degree field of view at just shortly after impact for our instruments. And what's important about this is that field of view, that red circle, is almost completely filled with ejecta cloud. That's important because that is filling the instruments with the signal, with the light, the information we needed to understand what was in the ejecta cloud. So it worked really well. We picked the time, the fields of view, and everything else like we had hoped, and it worked. We actually filled the instrument with signal, which was really important. The next slide shows some of my favorite bits of data from the mission. At the very end, we turned one of our near-infrared cameras to a long exposure, and as streamed down into Cabeus. Dip below the bright rims, what we saw was a floor of Cabeus revealed for the first time in 1 or 2 billion years. We have not seen the floor of Cabeus ever, of course. It's in permanent shadow. But these near-infrared cameras were able to image light that was radiating from the walls, scattering in from the rims of the craters and whatnot, and revealed what you see here. And eventually, what we could see, both in our thermal cameras, we could pick up the heat from the impact, and also this image, we could register them together. We could see the crater, the brand new fresh crater the Centaur had just made in this field of view. The arrow's pointing to it. What you see here are those bright hills. Those are nice sloping hills pocketed with smaller craters, some larger craters here. The scale on this image is a couple kilometers across or so. It's about 4 kilometers above the surface when we took this image. And you can see our crater down there with the arrow pointed. And the next image shows that crater zoomed in, inset. We hit into a nice level flat plane, which is exactly what we wanted. It is one of the coldest places in Cabeus. The Diviner instrument saw our impact crater as well on the LCROSS spacecraft and measured the temperature in the region where we impacted at about minus 230 degrees, 220 degrees below 0 Celsius, so very, very cold. And you can see in that inset the crater we made. The dark area in the center is the crater. The brighter area is ejecta that has been spilled out across. The crater we made was 20 to 30 meters across, and the ejecta, the bright area there, is approximately 60 to 80 meters. We have information that indicates that the ejecta blanket actually went much broader, out to several hundred meters outwards, really affecting the area. This is a nice, large crater. What we expected in the 20 to 30 meter class means we hit in relatively unconsolidated, weak material. And that's what resulted in the ejecta plume that you saw in the previous slide. So what did we see from the instruments that detected water? And that's what I'm going to talk about next. Next slide shows the 2 instruments that I'm going to describe in detail to you. The instruments that we're going to talk about are spectrometers. The spectrometers measure colors of wavelengths. And those colors are affected by various compositions from various compounds. For example, water or carbon dioxide or whatever. Each compound will affect those lights differently. We have 2 instruments that we used on this mission to look at that plume. An ultraviolet invisible spectrometer, the one indicated there on the lower left, and near-infrared spectrometers. We had 2 near-infrared spectrometers, one looking down and one looking to the side at the sun. Today I'm just going to talk about the 2 that we're looking down, because those are the 2 we focused on to provide the results I'm describing today. The next slide then shows some of the near-infrared spectrometer results. Unfortunately, spectrometers often just give squiggly lines, not pretty pictures. However, these squiggly lines are really important because they are, as I mentioned, the change in these colors and the changes in those lines really tell us what we're seeing in that cloud. What I have here is a plot of brightness against color or wavelength. And the black line with the little hash marks, the vertical hash marks, is the data, the observation. This is an average of about 20 to 60 seconds after impact. We've averaged a number of instrument scans together. The black vertical hash marks are uncertainty bars, or error bars in the measurement. Why I show those is to show that these measurements, these dips you see in the line, are real. They're not just noise, they're very real. And what you would expect to see if you're just looking at bright, colorless gray dust of ejecta is shown on the next slide. This red line shows a continuum, a black body, what we call black body continuum, something hot. If this is warm dust coming up, at about, say, 400 or 500 degrees Celsius, you'd see this nice red smooth line all the way across like you see here. That's not what the data sees. Data it kind of comes up and meets that line, but then it has all these notches taken out of it. And each of those notches is a compound, some kind of material absorbing infrared light, near infrared light. So the first thing we did was, well, let's put in some water and see what happens when you put water into that model, that red line. And the next slide shows that. And we get a good fit in two regions. The two regions are indicated by the yellow. Those are the water bands, water vapor and ice bands. There's actually a third to the left that I don't show here at about 1.27 microns, shorter wavelengths to the left, that actually shows this as well. We got good fits. This was a unique fit, meaning we could not put other compounds in here and generate this same fit. So we were really excited. It was a pretty tight fit within the air bars for water vapor and ice. Now all those other bands and bumps there are of interest too, and we've been studying those. And I don't want to say too much beyond what I've already said on those bumps and wiggles, except the next slide shows that we can actually fit them all pretty well with a variety of different compounds. And that's when I said this goes beyond the water. It really does. There's a lot of stuff that came out of there. And you're going to hear about this a little bit more as we discuss this on the panel. But there was a lot of stuff that came up out of the floor of Cabeas, not just water that we saw. So the next slide then goes on to the next instrument. If we can have the next slide. This is the ultraviolet visible spectrometer. And what's really important to consider today as I come forward with these findings is we see evidence for the water in two instruments, two independent instruments looking at water two completely independent ways. And that's what really made us confident in our findings right now. This shows the radiance, or the brightness, measured by the ultraviolet visible spectrometer. Again, it's measuring the brightness as a function of color. And that's color or wavelength is shown across the bottom axis here. The red line shows the measurement. So it's a little bit brighter towards the right at red wavelengths. 660 nanometers are red wavelengths. What you see, though, that's important are some little spikes. Those little spikes are called emission lines. Emission lines are diagnostic of a variety of different compounds. So, and they result from when a compound, either a molecule or an atom, is in an excited state and relaxing out of that excited higher energy state. It releases some of the energy in the form of light and creates a sharp spike, an emission line. You can kind of think of it like a neon sign that's glowing red and has a particular gas in it, gets excited, energized with electricity, and as those atoms in that neon bulb relax, they emit light of a particular color. That's what we're seeing here is species are emitting light at a particular color. And by understanding exactly what color that emission line is at, you understand what species is emitting it. So what we were interested in is some emission lines in the ultraviolet. And if we go to the next slide, we can talk about those emission lines. The emission line we were interested comes from the hydroxyl molecule, OH. OH can be produced when water vapor, H2O, is broken up by sunlight. Ultraviolet sun rays will break up a water molecule into OH and H. And that OH is energized, it's excited, and as it relaxes from an energized state, it releases some light, an emission line, a series of emission lines even between 306 and about 310 nanometers in the ultraviolet. And that's the range we're looking at here. So what this figure shows is the ratio. What we've done is we've divided pre- and post-impact measurements to get rid of everything else we're not really interested in. We're just interested in stuff resulting from the impact, and plotted it as a function of color again here, or wavelength. And right in the middle where that blue color is, you see a spike that rises from earlier scans, which are down near the bottom, to later scans, which come up in ratio at time. And there's two things occurring here. The lines near the bottom are relatively flat in lower levels. Those are basically pre-impact scans. What those show is they're flat, not a lot going on there, and they're at a lower level. After the impact, we had an ejected cloud come up. It was scattering sunlight, reflecting sunlight, and that's why the levels in general come up higher and higher. What you can see then are spikes emerge in a variety of places, but the one we're interested in for today's discussion is right in that blue area. And you see a sharp spike come up right around 309 nanometers or so. And I've highlighted a couple of those spikes with green, showing the height of those spikes. We call the band strength. That is the strength of that OH emission line and the brightness of that emission. And that's related to how much OH is there and hence how much water is there. So by one seeing this, it confirms that there is water being photolyzed, being broken apart by sunlight above the ejecta cloud or within the ejecta cloud in the field of view of this instrument. What we can do then is take that strength of that line and plot it over time and actually use it to figure out how much water was actually there. And in the next slide, that's what we show the strength of that band as a function of time. And you can see in the yellow area, the pre-impact period, that band strength is relatively flat within the noise of the system. And shortly after impact, you see it rise up fairly quickly and then stay steady over 2 or 3 minutes with some variations over time as we flew in towards the cloud. This is really a good detection. It's a strong detection, well above the noise level. So this, combined with the other infrared absorption lines, the dips I showed you earlier, are two very strong independent indicators that there was water vapor coming up out of Cabeus and other things as well, as I mentioned. So using both those measurements, when I opened with the amount of water we think we saw, we can constrain right now how much water we think is in the field of view of our instrument. And that's what I described. There is, based on these measurements, there is more than 100 kilograms in the field of view of our instrument. What does that mean, 100 kilograms? That's the dozen or so 2-gallon buckets I described. But what we need to do next is actually take all the information, the amount of ejecta, the size of the crater, how this all changed over time, and actually reconstruct the entire event, understand how it all fits back into the ground, along with all the other things that we've seen in the ejecta plume, to really understand this whole thing in its entirety. I think what we're presenting today is a status update, where we are. It was, I know, very important to the public to know the result of the LCROSS mission, so we were very compelled to work as hard as we could to come out with the results when we did, after the team was confident and had a consensus that what we found was indeed water, and we could give some kind of quantifiable amount. The last slide again shows the immediate science team who's been working on this result. A very small team, focused, dedicated, and I just got to say thank you to them for doing all the hard work that you've seen presented today. And there's much more that will be presented in the coming weeks and months at a variety of venues. So with that, I will turn it over to Greg Delory, who will provide some context for this observation. And Greg, thank you.
Thank you. First of all, let me join my colleagues here in expressing to you what an exciting and extraordinary discovery this really is in our understanding of the moon. What I'm here to do today is to try and give you some idea of the importance and significance of this new finding in the larger context of lunar science and in our understanding of the history of the solar system. So let's talk about polar regions. One might start with the question, why are the polar regions so important? And one way to convey that is to use an analogy. Many people may be aware that some of the best information we have about our own Earth's climate, in fact, comes from a detailed analysis of polar ice cores, things we get from our own poles in the Arctic and Antarctic. And in very much the same way, the lunar poles are sort of record keepers of conditions throughout the lunar history and throughout the solar system's history for very long periods of time. And this is because the surfaces in these regions, in these permanently shadowed areas, such as the one that LCROSS impacted, are very cold. That means that they tend to trap and keep things that encounter them, compounds, atoms, and so forth. And so they act as record keepers, perhaps over periods as long as several billion years. So they have a story to tell about the history of the moon and perhaps about the solar system climate, if you will, conditions in the early solar system that are unique to these regions. Second of all, let's talk about water. The focus of today's press conference has been water. Water is very important. It's what scientists call a volatile. That means it's a compound that's very easily mobilized by changes in conditions such as temperature and other stimuli. It's very sensitive to thermal conditions, radiation, bombardment history, and so it's sort of a record keeper in that sense, in that it tells you something about the history of the region from which you obtain it. It's also been suggested that if we find water in large enough amounts, and I just heard 12 buckets full, it's possibly a resource for human exploration if human settlers ever go there. So for these and other reasons, water is of extreme interest on the moon and also other planetary bodies. So getting on to some of the potential significance of this result. As I said, LCROSS has made a major discovery. A decade ago, we knew from lunar prospector measurements that there was a large amount of hydrogen in the polar regions of the moon. Unfortunately, we had no idea the form of that hydrogen. Because of its location, because it was in the polar regions, a very easy assertion to make was that it was in the form of water, probably ice. But I think because of the ambiguity of the measurements, there was no firm consensus in the scientific community that it was in fact water. LCROSS has now made that definitive discovery. It's very likely that a lot of that hydrogen is in the form of water. And so now we can move on to much more important and interesting questions. And so while this discovery is significant, what's equally important is what we do next. And some of the really intriguing questions that come up are the following. Where did the water come from? How long has it been there? What kind of processes are involved in putting it there and modifying it and removing it and destroying it? It's when we get at these processes that we'll begin to understand the story that the lunar polar region has to tell about the moon's history, about our own history, about early conditions in the solar system. So some examples to whet your appetite in terms of the stories we may learn. One possible source for the water is from comets. The moon has been impacted by comets in the past. And if that's true, and the lunar polar regions really are repositories for this material, that means that they are a literal treasure trove of information in terms of the composition of comets, which are themselves indicative of early solar system conditions. That would be of extreme interest to many planetary scientists. Another possibility, completely different. Water could come, in fact, from the solar wind, which is basically an ionized gas streaming off the sun, composed mainly of hydrogen. It impacts the lunar surface, undergoes chemistry. Eventually, these molecules hop around the surface of the moon and end up concentrating around the poles because they're cold traps. They trap everything that comes their way. In which case, studying those deposits would tell us something about solar history, also about the history of chemical reactions occurring on the surface of the moon. Two completely different theories. We don't know which one is right yet. Other sources are also possible. Giant molecular clouds have passed through our solar system many times in the past. They have hydrogen-bearing compounds. Ice-laden dust could be raining down. Another intriguing possibility is that the moon itself may be the source of the water through internal activity. And so analyzing that deposit would give you a window into the interior of the moon. The Earth itself could also be a source. So I'm summarizing all these to give you a preview of the kinds of stories that the lunar polar regions could possibly begin to tell us. And now that we know that water is there, thanks to LCROSS, we can begin in earnest to go to this next set of questions. So in summary, this recent result from LCROSS, together with emerging results from the Lunar Reconnaissance Orbiter, ongoing lunar program, are really exciting. It's painting a really surprising new picture of the moon. One way to state this is that this is not your father's moon. Rather than a dead and unchanging world, it could in fact be a very dynamic and interesting one that could tell us unique things about the Earth-Moon system and the early solar system conditions. I'm sure the LCROSS team is going to reveal new exciting discoveries as they continue to analyze their data. We also have the NASA Lunar Science Institute in place with many scientists who are poised to help answer these questions. We have exciting upcoming missions such as the Lunar Atmosphere and Dust Environment Explorer, which will help determine if there are active present-day processes that are moving water around the surface of the moon. It's going to be a very exciting time as we begin to learn about this new emerging picture of not just any moon, but our moon. And so with that, I'm happy to hand the discussion over to Mike Wargo of the Exploration Systems Mission Directorate.
Thanks a lot, Greg. Well, there you have it. We've discovered significant quantities of water in a permanently shadowed crater on the moon. Now, an awful lot of you wanted us to be able to say that a couple of hours after impact, and we weren't just able to do it that day. And what this is an example of, I'm going to rewind the clock just like Tony did and go back to that day. There's this healthy tension that exists between a really interesting and exciting story that you want to tell, but then not necessarily having the confidence in what you know yet, because you haven't had a chance to go through the kind of analysis that scientists do as we develop this story in a compelling way. Well, this is another step along the way. We were, you were frustrated that day, we were frustrated that day, but now we're starting to be able to tell you more and more about that story, to the point where we have water in these permanently shadowed craters, and we also are seeing hints of other stuff that's there. And Tony gave an example of those wiggly lines getting fit better. But we have to go back and look at what does it take and what is the uniqueness of the solution to those kinds of problems. By uniqueness, I just mean, can you get a set of chemical compounds that only that set in only those in the concentrations give you that line? That's how we were able to come to the conclusion that that's water there, because if you didn't have the water, you couldn't have fit those lines the way we did. Now, we're excited today, you can definitely tell that, but it's for a whole lot of different reasons. I'm going to go back once more to the importance that this mission has for both exploration and science. Greg did a great job of telling the impact that this has on adding to our understanding of the moon and the solar system and the dynamic nature of the moon as a planet. Who just a couple of months ago would have thought that we're talking about not just water on the moon, but lots of water on the moon and the processes by which it gets there, by which it stays there, these cold traps. You know, they're really like the dusty attic of the solar system. They collect stuff from the whole evolution of the solar system to this time, at least over the last few billion years, and there's a treasure trove of information in there. And we've only just begun to tap that understanding. There's an awful lot more there, and it's there for science and exploration. Water can be used for, you know, the kind of things we think about every day, drinking water, if we have extended cruise on the surface. You can break it down and have breathable air for crews to breathe. But also, if you have significant quantities of this stuff, water really is the constituents of one of the most potent rocket fuels, oxygen and hydrogen. An important point, though, and each of us has said this, and I think I need to say it again, and this is only another point, another snapshot in time for our understanding of this wealth of information that's come out of the LCROSS measurements. We're going to be continuing to work to get more and more details about the other information that's not the water this time. So we're really not done yet, and we're going to keep you informed as we progress and as we find more and more information. But we're going to do it in such a way that we have the same kind of confidence when we talk to you next that we have today when we talked about the presence of water there and significant quantities of water. So we're going to be coming back to you, but right now from Washington, we have Doug Cook, our Associate Administrator for Exploration Systems, and Doug's going to give us his perspective on what we've told you today. Doug?
Thank you, Mike. We're happy to be here with you. I want to congratulate the entire LCROSS team, and particularly today the science team and all those who have helped to get to this point in understanding results from this recent mission. I continue to be very proud of this team. They began with a project that was capped in cost, so they had to work very effectively and very efficiently to get to the point of getting the spacecraft built, launched, and now to the point of getting results. So this has been a very well done effort on the part of this team. They faced some big issues just prior to their launch, and once they were flying in space in terms of getting the mission, keeping the mission on track and getting to the point of impact. The precision of the impact was incredible. The instruments performed exceptionally well. And now we're seeing remarkable results that are beyond expectations. The discovery of water, ice on the moon. This is something that's been in question for quite a few years now. This is ice that's potentially been there for billions of years. It obviously has implications for science in terms of understanding the history of the Earth, Moon system, and the solar system, and the implications that were described for exploration in the future as water as a resource for explorers in the future. So many have said that we learned most of what, or all of what we needed to learn about the moon from the Apollo missions. LCROSS is demonstrating that there is much more to learn, and there always is. We also have the Lunar Reconnaissance Orbiter that is in orbit around the moon, collecting data and making high-fidelity 3D maps of the moon that will be of use in the future. So we continue to learn more about the moon. So stay tuned. The moon has more secrets. The further data from LCROSS will reveal some of these, as will data from LRO. I think it's incredibly exciting, and I'm really happy for what part I get to play in this. So thank you for the opportunity, and back to you guys.
Okay. Thank you, Doug, and panelists. We will now be taking questions. If you have a question, please raise your hand, and I will direct my colleagues with the mics. And okay, and then before asking your question, please state your name and your organization. Thank you.
Good morning, Matt Bigler, CBS Radio. My first question is, Anthony, with that moment when you discovered that there was indeed water on the moon, what you've been looking for, did you toast with water or champagne? And describe that moment to us.
Well, it was about, I think, about 3 a.m. when I was doing the fits. I mean, we've been working on this pretty much round the clock, and we were working through the data, and I was kept coming back to in particular, the 1.4 micron feature, that earlier dip, the stronger dip, and kept coming back to that. And I sent out to the team a post, and I said, I can't get rid of this dip. Can you get rid of it? And no one, and some of the other spectroscopists said, no, it's definitely real, and it's there. And so are all these other dips. And that's where we said, okay, this is all noise. We got to beat this down. That's the average. No, it's real. Okay. And that's when we kind of sat back and we said, oh my goodness, this is a lot more complicated than we had really anticipated, meaning it wasn't just water, but there was a lot of other interesting stuff in there. And then it was when we built some of our models and cleaned them up, and we walked through it as a group, we were like, okay, water does fit there. That's pretty good. But then it was when one of my colleagues said, you know, I think I see the OH line too. And she started applying, she showed it to me, and I said, okay, that was a eureka moment. I was like, I'm convinced there's water. I've got two independent people working independent problems, and they both came to the same conclusion. And then we vetted it, and we vetted it, and we vetted it, and then we vetted it some more as a team. And it was supported, it's corroborated with a number of other observations too. So we have not had time to enjoy it because we're so interested in everything else that's in there. And we've been working really hard just to pull it all together. I'm sure I'll be doing some toasting now, though, that I can speak openly about it.
I'll ask a serious question real quick. Is there enough water so that astronauts can live off the land on the surface of the moon? That's
a matter, I think, of where we're going to take this work in the future. You know, we hit one place in Cabeus, and we went there because all the data said there was a lot of hydrogen there. And I think the number I'm giving right now is probably a lower limit. And as we refine our analysis, we'll be able to reduce the uncertainty in how much water is there. If you take that and then you take the observations of hydrogen from Lunar Prospector and from the LEND instrument on LRO, we can extrapolate to what exists globally on the moon. And I think it's going to be significant, but there's going to be as you take one spot and you extrapolate it more broadly, there's going to be, associated uncertainty that we have to understand. I'll put it this way, I was impressed by the strength of the bands, so I'm pretty impressed by the amount of water we saw in our little 20-meter crater.
Okay. Okay. Hold on a second, please. Take the mic.
You made a reference to other things that might be out there. What's the range of possibilities?
Some of the things we're looking at, and this is just things we're considering, because as Mike said, the uniqueness is important, are a variety of other CH molecules. So, and one of the things I did early on was compare our spectra to some primitive icy bodies like Centaur or Trojan asteroids. And there was a considerable amount of similarities. And so on those bodies, you'll find CO2, methane, SO2, perhaps other things like ethanol, methanol, organics, things like that. Now, all those are possibilities, but we need to really do the work to see which ones fit best. You saw one fit that we were able to come up with, which combined a variety of those species, but it's certainly that it is certain that some of those species are in there. Which ones is what we need to figure out going forward.
Yeah, it's really a question of how many different kinds of combinations of things can give you that same set of squiggly lines. And do you have other ways of understanding the data that gets you toward that uniqueness, so that's only one combination of compounds at certain fractions that you're confident in?
Okay, well, go. Please state your name and your organization.
Mike Meacham with Aviation Week. You've been talking just about instruments that were on the shepherding spacecraft, if I understand correctly. And you had a lot of other instruments from the ground observatories as well as other spacecraft. Have you started to how much have you started to overlap, if that's the proper word,
right.
their data with what you've got, and can you give us an idea of where they are in helping you?
We're working very closely with LRO. LRO, of course, helped us guide us to the spot. So, this is as much to their credit as anyone, and to find the spot in Cabeus. And then two instruments observed the impact on LRO, Diviner and LAMP. They have very exciting results. We've been working very closely with them. They've been participating in some of our team meetings, and we're writing up our results together. I don't want to speak too much to their results because that's their results, but it is incredibly complementary in a lot of ways. Not saying that they see water, I'm not saying that, I'm just saying it's very complementary, and that they're going to help constrain all of our measurements and vice versa. For ground-based observing, Earth-based observing, most of all the observatories made great observations. They were on target, but they knew it was going to be a difficult observation once we moved to Cabeus from Cabeus A. Cabeus A had the best observing for Earth-based observatories, but after continued observations from LRO, which said the scientific relevant place is Cabeus, that combined with our instruments working well on our spacecraft and LRO phasing its orbit to make the observation, I consulted with the ground-based observing campaign, and I said, I want to move it to Cabeus. It's going to hurt your observations. They said, we understand. We're going to make them anyways. That said, they saw some interesting things, and they are working on analyzing it now. A number of observatories saw emission lines from sodium rise up high over the impact site several minutes after the impact. So others have seen changes in the scattering continuum, and meaning that they may have seen some dust come up. Others have seen changes in their spectra, but they have a much, much harder time than we do in understanding that data. The experiment was set up perfectly for our shepherding spacecraft. We were flying directly down at the impact site. He had a dust cloud against a perfectly black background. It was optimum for us. For them, they had to look over a hill, to get at the ejecta, and any gas that came up was quickly was moved quickly in front of a bright moon, and so it made it that their observations difficult. Their status right now is they're still analyzing it, and they're probably going to report in the springtime, I would think, as to their findings.
One of the, I've heard various estimates of is how close you came, 40 meters, 1,000 meters. How close did you come to perfect targeting with the Centaur?
We are, well, so we had a 3.5 kilometer goal on the science team. We smashed that, I think. We're still analyzing exactly where we hit, and right now the uncertainty is probably about 100 meters or 200 meters, but we hit within probably that. It was very close targeting where we wanted to hit.
Okay.
Tony, Wayne Friedman, ABC 7 News in San Francisco. You talked about water and you talked about ice. If you were to melt that ice into a beaker, what kind of water would it be? Would it be water you could drink?
Well, if there's methanol in there, I wouldn't drink it because it'd go blind. But it would be water that you could drink. It's water like any other water. I don't think, we still need to really sort out the flavor of the water, meaning how much is ice? Is it crystalline ice on the grains, or is it just vapor coming off adsorbed water? We still need to do that math. That's going to take some time. Right now, based on the amount, I don't think it could just be adsorbed water, meaning, and by adsorbed I mean water that is just formed in films along grains boundaries. I think there's too much. Some of it has to be ice. We're sorting that out. And if you could clean it, it would be drinkable water.
When you talk about ice, you were talking about a frozen lake in the ideal.
Well, yeah.
Can you typify what you think you hit? And you say ice, are we talking about chunks of ice? Are we talking about ice within the...
That's going to come out in our studies, but based on, if I had to conjecture now, we made a nice crater, meaning we didn't hit something that was frozen. And so that says a lot about the state of the material that we hit. That will combine that information with the amount of water we derive from our spectroscopy, from our measurements, and come up with some kind of ideas of how it's distributed right now. I don't know. I think it's safe to say it wasn't a frozen lake. All the water wasn't on a perfect surface at the top on a frozen film. But it was probably intermixed within the grains, frozen granules and whatnot. That remains to be seen, though. I mean, that's some of the ongoing work we need to do, really taking all the data sets and combining them into one story.
If a person were to stand there, what would it look like? Would it look different?
I don't know. That's a good question. We've been talking about that, and based on some of the observations, it would be an interesting place to walk around, I think. Some of these species that we're talking about are fairly volatile other than water. We hit a very cold place, minus 220 degrees below 0 centigrade. But some of the species that we think we may be seeing are fairly volatile. So meaning you don't have to warm them up much, just by 20 or 30 degrees, and they're going to bubble off. We do have, what's fantastic is we have these near-infrared camera images of the Florica bays. So we actually can relate those to what the human eye would potentially see. And so that is in our plans, is we have these images that we never really anticipated having. We're going to go look at those very closely, understand the reflectance, and understand exactly what the terrain looks like. That is important, actually, to understanding what it is we hit.
Are you saying you saw water before impact?
No, we're not saying we never saw the floor of the crater before impact. We only saw it once we got way down low after the impact. But the brightness of the terrain where we hit, we can actually understand that and say something about what the floor looks like.
Okay, thank you, Wayne. Do you have any other questions in the audience? Okay, we have one up front here. We have one up front.
Yeah, I guess if you can talk about the thermal characteristics of the impact and water versus ice and the 12 buckets and how much got evaporated or went into vapor and that sort of thing, and anything about the characteristics after the impact of the cloud. Did it all go off, or did some of it come back, or?
Sure. Yeah, we. It was as one of our co-investigators put it, it was a tepid impact, meaning cold in his experience. Meaning it was probably about 1,000 degrees Kelvin, or about 700 or so degrees Celsius, and that's cold for impacts. But that's kind of what might be expected with a low-density rocket, impacting fairly slowly. There is evidence for a vapor and debris cloud that came up at a very sharp angle, very early or immediately after impact, that rose very quickly and got to altitudes above the crater rim within seconds after impact. And at the same time, a lower angle, more traditional ejecta curtain came up laterally outwards, and that's what we see actually in the image is a lower density plume coming straight up at us, and then a higher density plume coming out to the sides. All of that returned back to the moon, and there's evidence for actually that falling down in the area around the crater of several hundred meters to a kilometer out around our impact site. There's actually indications of that. In our thermal imaging, what was great is our thermal cameras could measure the impact plume temperature all the way down, and then we can measure the temperature of the crater, and that's where we're getting some of the estimates. At the 4 minutes after the impact, the crater temperature and some of the debris blanket around the crater was still minus 40 degrees, minus 50 degrees centigrade. That's warm when you're talking about it's sitting on top of dirt that was originally minus 220 degrees centigrade, right? So, and all these things we're talking about here, including water, are unstable at those temperatures in a vacuum. So that really is part of the equation or puzzle we're piecing together. There's this ejecta and plume that came up, and there appears to be a vapor that was entrained in that as part of that came up very quickly. So that was the initial impact. And then there was a continued release, perhaps, maybe, of vapors from the floor. And then the ejecta came into sunlight, and there was any ice grains mixed in with that dust and the ejecta in the sunlight, it would have warmed and would have come up as well, released and volatilized as well. The one thing I can say is it's very complicated, very dynamic, and very fun to study. But yeah, we are having fun, but it's very complicated, and that's what we're going to do is piece together this whole storyline of everything that occurred. Yeah.
Okay, thank you very much, and we will now take our first phone call. Richard Kerr from Science Magazine. Go ahead, Richard.
Thanks, Jonas, but my question has been answered. Thank you.
Okay. We'll now go to Irene Klutz from Discovery News. Irene?
Thanks very much. It's Irene Klotz with
Klotz,
Discovery.
fine.
That's okay. Tony, before the impact, you had painted out 3 different scenarios of what you thought might happen, including one which it sounds like you may have kind of decided on and used the analogy of the raisins in the pudding. Could you talk about if this was did you just hit a jackpot and other areas of the moon may not be like this, or do you really think that this is indicative of some kind of overall environmental condition on the moon? Thanks.
Yeah, good question. And I think that's something we'll have to answer in time. It's not something I think I can answer right now. But we will exactly do what you're bringing up, is take what we learn from this and then apply it to the potential models. And you heard Greg talk about that in terms of what are the next step now that we know that there's water, and once we actually study this impact some more and understand how that water may have been distributed and what other things may be involved with the water. There's chemistry that can be discussed, there's distributions, there's sources and sinks, and we'll get to exactly that question you had is did we hit in something typical or atypical? That's a good question. I don't know the answer to that just yet. And then how does it relate to the rest of the moon? Those are all things that I think are going to come out going forward.
If I can make a comment.
Yeah, please, Greg.
This is Greg Delory. I think you bring up a really good point. LCROSS is sort of pointing the way, now that we know there's water there, it's really important to understand how it's distributed because that'll give us very important clues as to its origin. What I think this is pointing us to, and I think we're going to see an increasing interest in, is actually going there with a robotic mission and actually understanding on site how the water is distributed. If I can just make a plug for where we might go in the future lunar exploration program.
Okay,
Thank you. I also had one other question about the possibility of organics. I think you mentioned that briefly when you were giving your laundry list of what could be mixed in with the water, but could you specifically just talk about the significance if any organics are found in this plume? Thanks.
Sure, and that was a laundry list. I don't want anyone jumping to conclusions just yet. I mean, I'm speculating as what could be in there, but it's hindsight's usually 20/20. And if you have some place as cold as what we hit, and you've had comets and asteroids and interplanetary dust grains collecting there for 1 billion, 2 billion years maybe, it's actually quite reasonable you'd find everything I just listed in that hole. You know, as Dust put it, as Mike put it, it's like a dusty attic. Actually, it's not too dusty; it's a little wet. So the significance is then getting at what Greg brought up is where did this stuff come from? And I think that's the question: is if indeed we find organics, and if they're a particular flavor of organics, that says, well, maybe it's cometary. There is at least some cometary contribution, or if we find something else like methane, or what does that mean chemistry-wise? Can you actually make methane from the solar wind? If not, well, then it's got to be coming from someplace, and what's going to come out ultimately, I think, from the LCROSS mission is the first hints, first clues, or additional clues to the broader data set is a better way to put it as to what's going on the moon.
Okay, thank you very much, Irene. Now we have Nancy Atkinson from Universe Today. Nancy?
You mentioned sodium earlier today, and the day of impact, you said that was the one surprise that you saw in the initial spectroscopic data. Have you been able to find anything more out about that and what it might mean?
Well, it's again, it gets to the last question. Is I think there's a little bit of everything in there. When we hit, we certainly saw sodium, and it was ground observatories saw it as well, and they saw it at fairly high altitudes. This is part of this potential plume, this high-angle plume that came up and got very, very high. We see other emission lines that we have not yet completely identified in our visible spectrometer data set, and we're still working on those. So, no, I don't know what all else is in there just yet. We've been really focused on the water question because that was our scientific goal on this mission, but we're going to get to some of those other questions soon.
Yeah, if I could make one additional point on this, and that is that we're talking about, whether it's cometary or these other things or another mechanism that the list that Greg went through. It could actually be all of those. And we could be seeing is a mixture. It's not just an attic, but it's a junk drawer. It's got everything in there. And so part of the resolution of this puzzle is to try to unravel this level of complexity that we're finding there to try to say which mechanisms could be in place. And I think we're all expecting that it's not just one.
Right. And I should say sodium is one of the more observable gaseous species in the lunar atmosphere. So we know sodium's mobile. We know it's a part of the processes that exist currently on the moon. So it's not necessarily too surprising that you would have something that is mobile, like sodium, gathering in concentration in some of these dark craters, and we released it. And so now we need to actually step back and say, well, what else could be in there? Actually, this is very interesting. The moon is alive and it's mobile, and these places are places we can look for some of this stuff and understand it.
Okay, thank you very much. Now we have a question from Andrea Thompson from space.com. Andrea?
Hi, I was curious how, or if you can really sort of combine your findings with what the Chandrayaan found with the signatures of water all over the moon, and does that tell you something more about the source of all this water?
Sure, I can take that, but then I think each of the panelists here can comment, both Greg and Mike as well. What Chandrayaan saw was primarily this hydroxyl OH that was bound in grains, as well as some adsorbed water, kind of monolayers, just single atomic or molecular layers of water, in probably the top few microns or so of regolith. They could not see into the shadowed craters, so their observation is entirely unique and complementary to what we did. We looked inside the permanently shadowed craters where they couldn't look, and the amounts that we saw and the flavors that we saw could be distinctly different, meaning they saw water bound in grains and maybe absorbed on grains. We saw potentially real crystalline water ice and lots of water vapor, meaning it came from something probably in addition to the adsorbed water, it probably came from water ice. And we saw these other species that I've mentioned. So they're kind of two bookends. They're two facets of the total puzzle here that we're trying to unravel. So they're really complementary. And I think there's the other aspect then we need to understand is how those two bodies or those two observations communicate with each other, and that's through the atmosphere of the moon perhaps, and through then delivery processes from other species and whatnot. So I think Greg you might want to comment on that.
No, I mean I think Tony's framed the question very well. It's important to note that while this is exciting, with LCROSS discovering large amounts of water, within the regolith, within the soil, a bunch of us were already reeling from an earlier discovery from M3, which discovered, as Tony described, a very thin layer of superficial water. And so the question becomes, how does this fit into the overall water picture on the moon? And I'll say right now that there could be no relationship between what M3 is seeing and what LCROSS has found. That's more of a static moon, okay? But it's also possible that the water that M3 found is sort of already on its journey towards the poles in an active process, and that really describes some of the variety of ideas that we're trying to work with here. So as I said earlier, it's just a very exciting time. We have all this new data, and now we're going to work through it and try and figure out exactly what the moon is telling us. And so I think that's just incredibly exciting.
Yeah, I think that one of the hallmarks for today is complexity. What we're seeing is a fairly complicated puzzle, potentially, with a number of different facets. One of the things that we found out from LCROSS is with the water that's present in the permanently shadowed regions, that could be one of the endpoints for the hydration cycle on the moon. That once things hop into these very, very cold permanently shadowed craters, they can't hop out again. So you can think of it as a sink. And there are a number of potential different mechanisms for the water to show up at the moon, and a number of different transport mechanisms that can move it around the moon. And what we're seeing from both the Chandrayaan measurements as well as the LCROSS measurements is a much bigger, potentially more complicated picture for water on the moon. And if you just step back not more than a few months, who would have really thought that we'd be talking about a hydration cycle on the moon? As Greg indicated before, this is not your father's moon. This is not a dead planetary body, but one with an awful lot of dynamism in it. And that dynamism really engenders an awful lot of new questions and interest in our closest neighbor.
Okay, thank you very much. Our next question is from Peter Spotts of the Christian Science Monitor. Go ahead, Peter.
Yeah, thank you very much. I'll try and squeeze two really quick ones in here if I can. First of all, thinking back on the Chandrayaan, LRO, et cetera, et al. Results, they were able to, at least in a back-of-the-envelope way, relate that to a concentration. I think it was something like you'd have to process a ton of soil in order, in principle, to get a quart or a liter of water out. Is there a way to relate what you folks have detected to some sort of concentration, at least at the impact point?
Sure, and that is the ultimate goal, or one of many ultimate goals that we have set in front of us. We need to understand really the cratering process, how much was excavated, what we observed of that excavation to really get at that question. So I'm not going to yet put it was 10%, or whatever to that yet. What I can say is what I said at the beginning is within our field of view, we saw some water. The instruments had a narrow field of view. We saw some water. Within that field of view, if I took the water just in that field of view and added it up, it was greater than 100 kilograms. So if you recall, yeah, they had to excavate I think a football field to get a glass full of water or so. In our field of view, which is some fraction of the 20-meter crater we made, because there was stuff that went on outside of our field of view, we had about 25 gallons or so of water. So that's the total abundance we can talk about right now, but I can't yet put a concentration into as to the amount in the dirt just yet.
Okay.
That's going to take time.
And just quickly, sort of context that I think alluding to just a few seconds ago. We sent astronauts to the moon, and they came back with moon rocks that sort of took us, one sort of increment farther along in our understanding of the moon and its processes or geological processes than we had before. Can you sort of put this into that context? I mean, what, in terms of our scientific understanding of the moon, or at least the questions that are being raised, what does this represent?
Sure.
Particularly in contrast with the Apollo stuff.
Well, I was born July 16th, 1969, so I missed a lot of the Apollo stuff. But just joking.
I envy you. There
has been a lot of reassessing of that information actually as of late, and in particular with the M-Cube et al. Discoveries. I think people are going back and rethinking, was that contamination? They detected water, they detected methane, they detected some organics. They all wrote those off to contamination as they brought the samples back to Earth. Some of it could very well be contamination. We don't, but people are at least now re-examining those measurements. Remember, we landed very near the equator for the Apollo missions, and so much further away from the poles than what we're talking about today. And that's relevant too. So it matters where the sample's been collected, of course. But I think what this shows is we are really exploring a new part of the moon that we hadn't yet explored yet. With the orbiters that have gone ahead of LRO, and now with LRO and LCROSS, we're re-exploring the moon. We're going to places we hadn't gone to 40 years ago. And so it's just revealing another part of the moon, another aspect of the moon that we didn't entirely probably fully appreciate then. And Greg, you may...
No, I think you described most of it. I might put it in a little bit stronger terms. One of the scientists involved in analyzing early lunar samples was quoted recently as saying he was going to eat his shorts because this has really turned our understanding of lunar water on its head. It was assumed that the water that was found on lunar grains was terrestrial contamination. This actually comes not from just an assumption, but from a detailed isotopic chemical analysis. That in of itself may have yet another message for how terrestrial and lunar water may be connected. I don't want to go too far down that road here, but the point is that we should really keep our minds open about what the moon is telling us and not be afraid to revisit our assumptions during Apollo. So back to that same message, it's not Apollo's moon, it's our moon.
Yeah, and when you take a look at what's been learned since Apollo, Lunar Prospector with the measurements that it made indicating that there was this increased level of hydrogen at the lunar poles really showed us that there is a different aspect of the moon that we didn't know about during Apollo. And the continuing missions with Chandrayaan and with LCROSS is giving us additional information about this really mysterious area that we didn't know very much about, and we're only starting to scrape the surface now.
Thank you.
Okay, thank you very much. Our next question is from Mark Matthews with the Orlando Sentinel. Go ahead, Mark.
Yes, thank you, guys. If you could, real quick, tell me, how big was the plume eventually? What were the measurements in terms of height and width, and was it as big as you hoped it was going to be? Thanks.
You can never have too big a plume, right? So it was, in terms of dimensions, it was actually very much in line with our expectations. That one figure I showed, image, was about 20 seconds after impact, and it was about 10 to 11, 12 kilometers across in diameter, and that's what we expected. We could observe the plume in our images for about 30 or 40 seconds after the impact. Our spectrometers had detectable signal of the plume. As long as potentially 150 seconds, 2 minutes after impact, that's actually in excess of what we expected. So that's telling us something about the material we threw up, that this high-angle plume potentially had a lot of fines in it, smaller particles, and they lasted above the surface for a longer period than we had anticipated. This was, we had enough margin, so to speak, in our observations to account for all these potential variabilities. In terms of height, it certainly got into sunlight. That's how we can see the ejecta cloud, and the shadow line was about 1 kilometer. It's hard to really tell right now exactly how high something gets when you're looking straight down at it. But we are going to be able to actually constrain the height better going forward, combining some of our various observations. But it got 1 or 2 kilometers above the surface, just below the rim height, where it would have been very observable from Earth. That said, vapor did get as high as, or material vapor distinctly, got as high as 20, 30, 40 kilometers above the surface. And we know that from observations from LRO and from ground-based assets. So material did get very high, the vapor in particular. Hopefully that answers your question.
Okay, thank you very much. Now we have a question from Stephen Clark, Spaceflight Now. Go ahead, Stephen.
Hey guys, this is Stephen Clark with Spaceflight Now. I just have a couple of questions. First, how long did it take? Tony mentioned that eureka moment. When did that occur?
That eureka moment really came about 2 weeks ago, 2.5 weeks ago maybe. And last week we had a team meeting. Was that last week? I guess it was last week. Last week, Tuesday, Wednesday, we had a team meeting with LRO participating, all of our team participating, and we went through the entire data set, lots of good discussion, debate. And then on the second day, I had a session based on just the case for water, and we asked, is everyone happy with this result? Can we go forward with this? I want to say something as soon as we feel comfortable, and we basically had a vote, and people said, let's go public right now. And so at that point, it was a scramble to make slides, and so it was. Honestly, every day the day after impact, a number of us gathered, tired, got some donuts, got together, coffee, started looking through the data, and we all walked out of there with giant grins on our faces. The next day, someone would come up, did you see this in the data? Did you see? Every day, it was an incremental discovery in the data. And every day, still, we're finding things that are just, we're blown away that we actually captured, so to speak, about the impact. So it wasn't a aha moment. It's been pretty much been a holy cow moment every single day since impact. So.
And my second question, you mentioned that you found more water than you expected. I guess compared to the land and lunar prospector data. I think that was my understanding. Can you describe exactly, how much more water was there than land and lunar prospector would indicate?
Well, I think I said I was surprised by the depth of the bands, which relates to the total amount of water vapor, and maybe I was a pessimist, and so that's why I was surprised. I can't yet compare it to a retrieval from land or lunar prospector yet, because we haven't put it into the ground yet. We haven't developed a concentration yet, which is something that those instruments do. You know, they say there's 1 or 2% by weight water, equivalent hydrogen. We haven't done that yet. What I have been impressed with is that the bands are clear and strong and evident, and we have such good detection.
Yeah, and another important point here is that the footprint for Lunar Prospector was on the order of 100 kilometers, and the footprint for the Lunar Exploration Neutron Detector on LRO is about 10 kilometers, whereas the area that was excavated was only about 20 meters in diameter. So there are length scales here where if we try to judge too much and move across too far across these length scales, we could get in trouble because we're not sure of the uniformity that is integrated into the data sets for Lunar Prospector. And we have a real significant physical point for the LCROSS measurements, and that's going to fit into this larger picture, and we're going to have to be talking to those teams to look at the relationship between and among the data sets.
Thanks.
Okay, thank you very much. Now we have a question from Ann Ryman, Arizona Republic. Go ahead, Ann.
Yes, thank you. You had mentioned you're still kind of analyzing, the percentage of water that may be there. Is it still fair to say, I've heard the moon described as it's still drier than our driest deserts here on Earth. Given what you found, is that still a kind of a valid comment, or could that be perhaps wrong?
For the 20-meter crater we hit, if you were standing on that nice little beach that we hit there, if you remember the image, it was kind of this low, flat plains. For the numbers, the amount of water I've stated, it is wetter than some deserts on Earth. Now, those deserts, like the Atacama Desert, is exceedingly dry, but it would, I think, be probably safe to say that it is on par or maybe a little bit wetter than that desert.
Oh, and what was the name of that desert again?
Atacama.
Atacama, okay.
In South America, Chile. Atacama, excuse me. Thank you. Not to be mistaken with a snake. Yeah.
Okay, thank you very much. Now our next question is from Ron Cohen, Science News. Go ahead, Ron.
So before LCROSS crashed in, there had been a prediction that even backyard telescopes, 10 or 12-inch telescopes, could have seen the plume. So why do you think the plume was smaller or less bright than you thought, and is that why it took more time to extract the water signal?
Sure. It was as bright as we thought it would be, except it was behind a hill, basically. Based on our calculations, the brightness of the plume was on par with a magnitude 8 to magnitude 8 star or so per arc second squared, which is quite observable with a 10 or 12-inch telescope. The issue was when we decided to go to Cabeus, it required that ejecta get even higher than we had hoped it needed to before. So that was part of the issue. Another issue was this high angle plume. The material that got the highest was of lower density than the material that went more lateral. So a lot of the higher density, brighter material stayed on a much more shallow lateral course as it came up. And so while that was good for our instruments because it filled our apertures with a very bright material, it was bad for Earth-based observers, even regardless of the dish size or aperture size, because the material just didn't get high enough over the ridgeline of Cabeus to be very visible.
Okay, well, just to follow up, I mean, I remember when I was watching the event with LCROSS, it almost looked like nothing happened. So were you surprised, or it didn't look like there was much of a plume when people were watching it in real time, so to speak, from the LCROSS camera data?
Sure. I was not necessarily surprised. It was in line with our expectations for our cameras. We wanted a higher exposure our near-infrared camera that would have made it more visible. And we were hoping for that, but we were battling data bandwidth issues all the way down, trying to maintain our bandwidth. So we didn't get a longer exposure call-in at the time we should have, perhaps, to make those cameras a little bit, show the plume more clearly. I mean, going back to the cameras, we can clearly see the plume in the cameras. Real time, it just wasn't as obvious as it would have been nice to have, that's for sure.
Okay, thank you very much. And our last question is from David Hirsch of NHK. Go ahead, David.
Yeah, one quick confirmatory question, if I could. Just to confirm that the water was observed both in ice and vapor form as part of this?
I don't want to say too much about how much was water ice or how much was vapor. Right now, the strongest signature and the OH signature is just with respect to vapor. It's a sublimation and photolysis event for the ultraviolet visible spectrometer. That data is strictly vapor. For the near-infrared spectroscopy, that has water vapor in it and some ice, and exactly the exact concentration between the two needs to be refined. But yeah, there appears to be both water vapor and some ice in there.
And I don't know if Mr. Cook is still on the line, but this finding, how does that impact, if at all, the human spaceflight review that's going on within NASA at the moment?
Well, let me take that one for Doug. The information that we're getting here is and has been available to our senior management within NASA as we've developed it, and so the information is going to be available as a way to ensure that the administration is well informed for them to be able to make their decision. So we have the information, it's useful now and for the decision-making process, and it's also going to be useful in the future as we continue to explore.
The Augustine report, which as I understood it now a couple of weeks after reading it, I think one of the options they talked about was even bypassing the moon. How much more sexy, if you will, does the moon look to you now after these findings?
Well, as we find out more and more about the moon, we realize that it's not a closed book for lunar science and lunar exploration, but it's just the first chapter of the book that we were able to do in Apollo and up until now. And the rest of those chapters are yet to be written, and I think they're going to be really exciting chapters.
In conclusion, if I could, and follow up to one of the questions from my colleagues, the answer was that the moon is, the area that was impacted might be a little bit wetter than some of the driest deserts on Earth. And if that's the case, just for a popular audience, why does that have you so excited to find a place that's just about as dry as a desert on Earth?
Who's that question? Who wants to take that one?
Let me take a real practical point of view. If there's a choice of having no water available to you and a little bit of water available to you by comparison to our Earth-based environment, I'll take the situation where we have a little bit of water available because it's so valuable to us for so many different reasons. For the scientific reasons that Greg talked about, for the exploration reasons, that water could be the key to sustainability for exploration. So having it there is going to be extremely valuable to us, even if right now we can't go swimming in it.
Just to add a science perspective, one might ask what's so interesting about the driest desert on Earth, and yet the Atacama right now is a hotbed of scientific activity because it tells us new things about our own planet. By the same token, going to a region of the moon is going to tell us really exciting things about lunar history, the solar system history, and perhaps the Earth. Obtaining a sample, analyzing it. So just understanding the record that it keeps is just of incredible scientific interest, and I think that we're going to see an increasing priority in the polar regions as a result, in part because of the LCROSS discovery.
Okay, and that's it. I'd like to thank our panelists and our audience here and watching on NASA TV and on the web. For the latest on the LCROSS mission, visit www.nasa.gov/LCROSS. And with that, this wraps up today's briefing. Thank you very much.